Hello and welcome to Quantum Mechanics Mathematical Foundations, Talk 1 Part B. My name is Jacob Hudis, and this is Quantum Mechanics the way I wish it was taught to me. And here's an outline of the talk. I'll begin with a brief introduction to skew-symmetric matrices. There will be a simple proof showing that the trace of any skew-symmetric matrix must be 0. And then we'll move on to learn that skew-symmetric matrices form a vector space. This vector space has a name called the Lie algebra. Now we get to the heart of the talk, which is the procedure to get the generators of SON via the exponential map. I'll do a detailed example where I compute the generator Rx of theta. This is one of the 3 generators of SO3. And finally, there will be an example putting it all together, finding the generators of the group SO4. And if you can do this and understand all of these procedures, then you're well on your way to being a quantum mechanics expert. Introduction to skew-symmetric matrices with examples. First of all, what is a skew-symmetric matrix? A skew-symmetric matrix is a square matrix, we can call it A, and it satisfies the condition A transpose equals negative A. These are examples of general skew-symmetric matrices. Skew-symmetric matrices have a type of symmetry where if you reflect across the diagonal, you get a negative of the number. So here's a 2 by 2 skew-symmetric matrix. The diagonal is all zeros in this case, and this number A, if we reflect it across the diagonal, you get negative A. This is a general 3 by 3 skew-symmetric matrix. All the reflections across the diagonal are negative. If you notice, this is B, you have negative B. C, reflected across the diagonal, is negative C, and D, reflected across the diagonal, is negative D. Here's an example of a specific 3 by 3 skew-symmetric matrix with numbers in it. All skew-symmetric matrices have trace 0. On this slide, I'm going to go through a simple proof to show you why that's the case. I should remind you of what the trace of a matrix is. The trace of a matrix is the sum of its diagonal entries. So if you notice, this matrix has trace 0 because 0 plus 0 equals 0. All the diagonals, all the entries down the diagonals are 0. That's the same for this matrix here. A skew-symmetric matrix does not have to have all zeros down the diagonal. It just has to have trace 0, which means when you add up all the diagonal entries, they equal to 0. This is a proof showing that. First of all, the definition of a skew-symmetric matrix is that A transpose equals negative A. And now if I take the trace of both sides of that equation, that tells me the trace of A transpose equals the trace of negative A. And the trace is invariant under transpose. Therefore, the trace of A transpose is equal to the trace of A. And so we know that the trace of A is equal to negative the trace of A, and that tells us that 2 times the trace of A equals 0. And this is a proof that says all skew-symmetric matrices have trace 0, and that's an important property that you should memorize. Another defining property of skew-symmetric matrices that is fundamental in quantum mechanics is that the exponential of a skew-symmetric matrix is an orthogonal matrix. In literature and in textbooks, this theorem is presented without a specific name. Any orthogonal matrix O can be written as the exponential of a skew-symmetric matrix. Specifically, if A is a skew-symmetric matrix, then O equals e to the A is an orthogonal matrix. So far, I've told you some properties of skew-symmetric matrices. First of all, a skew-symmetric matrix is a matrix with the type of symmetry, a negative reflection across the diagonal. A skew-symmetric matrix has trace 0, and the exponential of a skew-symmetric matrix is an orthogonal matrix. Shortly, we'll understand this by working out detailed examples. I just told you about the properties of the skew-symmetric matrices. There was a lot of information there, but hopefully you can take away that there's a type of matrix which is called a skew-symmetric matrix, and that matrix has a type of symmetry. Now I want to discuss something new related to the entire set of skew-symmetric matrices. The set of skew-symmetric matrices is a vector space. What this means is every skew-symmetric matrix can be expressed as a linear combination of basis matrices. There exists a finite set of linearly independent skew-symmetric matrices which serve as a basis for the space of all skew-symmetric matrices of a given dimension. For example, these 3 matrices are the basis for n equals 3. I'm just giving you these matrices. I'm not telling you where they came from, although it's not that hard. Once you see them, it's not that hard to figure out. The point is, linear combinations of these 3 basis matrices form any real 3 by 3 skew-symmetric matrix. And there are 3 basis matrices for n equals 3. This is an important formula. The number of basis matrices equal n times n minus 1 over 2, where n is the dimension of the space. To understand this idea, it's best to see an example. That's normally the way it works in physics. So we know that every skew-symmetric matrix can be expressed as a linear combination of basis matrices. Here's matrix A, which is a 3 by 3 skew-symmetric matrix. Therefore, A must be able to be written as a linear combination of the 3 basis matrices. And of course it can be. A is equal to negative J1 minus 3J2 plus 2J3. And I encourage you to check that on your own. On this slide, I introduce common physics terminology. These matrices form a vector space, and this vector space is called the Lie algebra. It's characterized in part by a property called the commutation relation. I won't delve into the commutation relations today. Instead, I'll focus solely on understanding the roles of group generators. This will prepare us for Lecture 2C as well as 3B, where I discuss complementary basis, maximally non-commuting observables, and the mathematics underlying the uncertainty principle. I have told you everything you need to know about skew-symmetric matrices. Now I'm going to move on to discuss how we compute the generators of the group SON. In Lecture 1A, I explained that any group can be represented by its generators. Understanding the group generators is crucial because they contain all the structural information about the group, which is essential for accurately modeling physical systems. For the remainder of the presentation, I'm going to focus on how we determine the generators of the group SON. I'm going to do this by walking you through detailed examples of finding the generators of SO3 and SO4. Next, I will demonstrate the procedure to compute the n times n minus 1 over 2 generators of the group SON. I'll do this using the groups SO3 and SO4 as examples. Understanding the process for one value of n equips you to handle other values. How would we obtain the generators for SO3? Well, the first step is we find the basis of matrices that make up the 3 by 3 skew-symmetric subspace. We're using the 3 by 3 matrices because we're dealing with SO3. The second step is to multiply each basis matrix by a rotation angle and exponentiate. The exponential of the basis matrices multiplied by a rotation angle produces the generators of the group SO3. On the next slide, I'll show how you turn this matrix exponential into a 3 by 3 unitary matrix. Now I'll do an example and demonstrate how to explicitly compute the generator Rx of theta by exponentiating the basis matrix Jx of theta. I will show that this expression yields a specific matrix. The convergence of this matrix exponential is facilitated by the unique multiplication properties of the Jx matrices. This is the basis matrix Jx. Jx squared is equal to this matrix, I'll call it I. So once you get to Jx cubed, you get Jx, negative I, negative Jx, I, Jx, negative I. Powers higher than 3 cycle through negative I, negative Jxi, and back to Jx. These properties of skew-symmetric matrices are sweet. They ensure the matrix exponential converges. Oh, what a feat. On this slide, I'm continuing with the example, computing the generator Rx of theta by exponentiating the basis matrix. This is the exponential, and this is the formula for the exponential. The exponential function can always be represented by this Taylor series. This series is often used in physics and is necessary for anyone studying physics to know. Any exponential can be expressed as this series without further explanation. If you're new to physics, familiarizing yourself with this formula will be incredibly valuable, as it underpins many key concepts in calculation. This is the Taylor series for the exponential. You take the identity matrix, then you take whatever's in the exponent. In this case, it's Jx theta. Then you add it to whatever's in the exponent squared divided by 2 factorial. So we have Jx theta squared over 2 factorial. And then you do plus Jx theta cubed over 3 factorial. And you just continue this process. And that's the Taylor series. Now in this particular case, the first term is the identity. The second term, Jx theta, is Jx theta. The third term has a Jx squared theta squared term in there. We know Jx squared is equal to negative the identity matrix. So this term is theta squared over 2 factorial times the identity matrix. The next term has a Jx cubed in it, but we know that Jx cubed is just Jx. So this term is theta cubed over 3 factorial times Jx. Here we have a Jx to the fourth, which is equal to negative I, Jx to the fifth, which is negative Jx, and so on. So now you can write the Taylor series in this form, which only has the identity matrix and Jx. It doesn't have any powers of Jx, Jx cubed, or Jx to any power. So what we can do now is group terms. We can group all the terms with the identity matrix, and we can group all the terms with Jx, factor out the identity matrix, and factor out Jx, and recall that this is the Taylor series for cosine of theta, and this term is the Taylor series for sine of theta. So then if I write cosine of theta times the identity matrix plus sine of theta times Jx, That's equal to this matrix exponential, and that's equal to this generator of rotation of the group SO3. This is the generator of rotation for rotating about the x-axis. Let's recap the problem we just did dealing with SO3. These three matrices form a vector space for the entire set of 3x3 skew-symmetric matrices. What this means is any matrix, any 3x3 skew-symmetric matrix, can be written as a linear combination of these three linearly independent basis matrices. Once we have the full set of basis matrices, we can multiply them by some rotation angle and exponentiate them, and that produces the three generators of rotation for the group SO3. RZ of pi over 3 is a rotation matrix that rotates an object by pi over 3 about the z-axis. This is that rotation matrix, and I can also write it as e to the pi over 3 times jz. This is a matrix, and this is a matrix. In quantum mechanics, matrices are often written as exponentials. It's done that way partly for convenience. On this slide, I want to have a brief discussion about how we define the 3 degrees of rotational freedom in R3. One can specify any point in terms of x, y, and z. One can specify any orientation in terms of a rotation about the z-axis, a rotation about the y-axis, and a rotation about the x-axis. It turns out there exists an infinite number of coordinate systems and thus rotation sets for specifying any point and any orientation of an object. For example, you can use the coordinate axes x prime, y prime, and z prime along with the rotations about these axes. Rotation about x prime, rotation about z prime, and rotation about y prime stays the same, and these also specify the orientation of an object. In order to do this, you need to do a change of bases, and that's the similarity transformation, which I'm going to go through in detail in the next presentation. I hope you join me for that. That'll be Quantum Mechanics Mathematical Foundation, Part 1C. And on to the final example, putting it all together, finding the generators of the group SO4. So in order to find the generators of the group SO4, the first step is to find the basis matrices that make up the 4x4 skew-symmetric subspace. These are the basis matrices. I'm just presenting them to you. Notice that there's 6 of them, and n times n minus 2, when you plug in n equals to 4, equals 6. And now that we have the basis matrix, we multiply them by some rotation angle and exponentiate them. After seeing the example we already did for the 3x3 case, it should be clear to you how this works. When we move up to 4-dimensional space, the concept of rotation becomes more complex. Here, rotations don't happen around a single axis, but rather within a plane of rotation. In 4 dimensions, there are 6 unique planes formed by pairs of the 4 axes. Here's a brief recap. SO3 represents all possible orientations in 3 space, with an infinite set of elements. SON has n times n minus 1 over 2 generators. For SO3, there are 3 generators. These generators define the rotational freedoms of the system. Understanding the group SON and how to obtain its group generators is crucial for quantum mechanics. All n by n skew-symmetric matrices form a vector space spanned by a minimal set of linearly independent basis matrices. This vector space is called the Lie algebra, by the way. The exponential of the n times n minus 1 over 2 basis matrices multiplied by a rotation angle produce the generators of the group. It's crucial to understand that while the matrix exponential is fundamental to defining groups like SON and SUN, the essence and more direct physical insight are found in the properties and actions of the generators. Avoid overanalyzing the matrix in its exponential form. Rather, focus on the inherent properties of the set of matrices that constitute the group generator. That is, the exponential of the basis matrices. This is a preview of the next presentation. Lecture 1, Part C. We're going to do change of bases and similarity transformations. AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.